Welcome to the tallest marvel on the planet, the Burj Khalifa. In the next few minutes you'll uncover 5 engineering feats that make this tower more than just steel and glass. Fact 1. The building's 30,000 cubic meters of concrete were poured with a high-pressure system that mimics a heart at 150 beats per minute, delivering a seamless, monolithic core faster than any skyscraper before it. Fact 2. Its iconic spiraling silhouette isn't just eye candy. The tapered shape slices wind forces by roughly 40%, letting the structure sway less than a hummingbird's wing during a desert storm. Fact 3. The double-deck elevators blast upward at 10 meters per second, zipping passengers to the 124th floor in under a minute, faster than many theme park rides. Fact 4. A massive chilled water network snakes through the concrete, cooling it during Dubai's blistering summer to prevent thermal expansion and costly cracks. Fact 5. The facade glistens thanks to a nanotech coating that repels dust and sand, meaning the tower stays pristine without daily washes. Each of these breakthroughs rewrites what we thought possible in vertical construction. But that's just the beginning. In part 2, we go deeper. Welcome back to our deep dive series on the engineering marvel that is the Burj Khalifa. In part 2, we move beyond the iconic silhouette and explore the sophisticated systems that transform a daring vision into a functional vertical city. The story begins in the late 1990s, when Dubai's Development Authority launched an unprecedented competition to create the world's tallest building. Adrian Smith, then a senior designer at Skidmore, Owens & Merrill, responded with a design that combined a sleek, tapering form with a core-centric structural strategy. His proposal won in 1999, setting the stage for a construction timeline that would redefine high-rise building techniques. By January 2004, ground was broken, and a colossal concrete pump was deployed to deliver self-compacting concrete up to 350 meters, the highest vertical pour ever recorded. The mix was engineered with silica fume and high early strength cement to achieve rapid strength gain while maintaining workability. This achievement required precise temperature control and a coordinated logistics network that sourced aggregates from multiple desert quarries. As the tower rose, the bundled tube system became the backbone of its stability. 8 reinforced concrete cores, each up to 2.5 meters in diameter, are encased by a lattice of outriggers and belt trusses, forming a hexagonal tube that efficiently transfers gravity and lateral loads. By interweaving these tubes, engineers achieved a moment of inertia that resists wind-induced sway, a critical factor for a structure that pierces the Gulf's turbulent boundary layer. Advanced computational fluid dynamics simulations, led by Arup's wind engineering team, predicted vortex shedding patterns and guided the decision to incorporate a 2-degree twist along the facade. This subtle rotation disrupts aerodynamic synchronization, reducing wind pressure differentials and minimizing oscillations. Inside the skyscraper, the mechanical systems are equally groundbreaking. A high-efficiency HVAC network circulates chilled water through a hierarchical series of pressure reduction pumps, allowing temperature regulation on each of the 163 floors with a 23% reduction in energy use compared to conventional designs. The curtain wall employs double-glazed low-emissivity panels that reflect up to 70% of solar radiation, mitigating heat gain while preserving panoramic views. Moreover, tuned mass dampers, concealed within the upper spire, counteract seismic vibrations and wind-induced motion, ensuring occupant comfort even during extreme weather events. These engineering choices have made the Burj Khalifa not just the tallest building, but also a benchmark for sustainable high-rise construction. The tower's influence extends beyond Dubai, inspiring a new generation of super-tall projects worldwide, each borrowing elements of its structural philosophy, wind mitigation strategies, and energy-efficient systems. As we reflect on these technical achievements, we recognize that the Burj Khalifa represents a convergence of architectural ambition, cutting-edge engineering, and rigorous project management, all orchestrated by a global team of specialists. In Part 3, we uncover what mainstream sources won't tell you. Imagine standing at the foot of the tallest building on Earth. The Burj Khalifa dominates Dubai's skyline, a shining needle that seems to pierce the clouds. Yet most people believe they understand its marvel, steel, glass, height. They are wrong. Beneath its glittering facade lies a series of secrets, each more astonishing than the last, hidden from the casual observer. In this third chapter we peel back the layers, exposing mysteries that engineers fought tooth and nail to conceal. First, the foundation. To anchor a structure that stretches 828 meters into the air, engineers could not rely on ordinary concrete. They drove over 200 massive steel cord piles, each plunging more than 50 meters into the limestone bedrock, past the shifting desert sand. But the real twist is the water cushion system, a network of recycled seawater tanks that continuously pressurize the piles, counteracting the relentless thermal expansion of the desert heat. This hidden hydraulic shield keeps the tower from sinking and from cracking under temperature swings that can exceed 30 degrees Celsius in a single day. Second, the wind. At such altitude, wind behaves like a living beast, gusts reaching 30 meters per second, capable of making the tower sway like a reed. The design team built a full-scale wind tunnel replica, 1:400 scale, and discovered a terrifying resonance that could have caused the skyscraper to oscillate dangerously. To defeat this, they installed a series of tuned mass dampers, massive concrete blocks that glide within the tower's core, moving opposite to the sway, dissipating energy. This quiet, invisible system remains unheard by tourists, yet it saves the building from catastrophic motion. Third, the elevators. Moving people 124 floors in under a minute sounds like magic, but the truth is a triumph of physics. The elevators travel at 10 meters per second, yet they must overcome the tower's changing pressure and temperature. Engineers devised a double-decker system with a regenerative braking network that recaptures energy on descent, feeding it back into the building's power grid. Moreover, the cables are coated with a polymer that expands in heat, preventing sagging. This subtle adaptation, concealed within the shafts, lets the elevators glide smoothly despite the tower's extreme environment. Each revelation reshapes how we view the Burj Khalifa not just as an architectural icon, but as a masterpiece of hidden engineering, where every bolt and pipe tells a story of relentless problem-solving. The foundation's secret water cushion, the wind-taming dampers, and the temperature-smart elevators all work together, unseen, to keep the tower standing tall against nature's fiercest forces. As the mystery deepens, the next part will unveil the final secret that changes everything you thought you knew about super-tall skyscrapers. Expect a groundbreaking discovery about the tower's spire that alters the entire narrative of modern construction. The engineers themselves called it the hidden spine of the tower. Stay tuned, because the truth is far stranger than you ever imagined. Now that you know the truth, Part 4 will change how you see this forever. Welcome to the final chapter of our 4-part series on the engineering behind the Burj Khalifa, the world's tallest skyscraper and a monument of modern ambition. In this masterclass, we will trace the tower's origins, dissect its structural and mechanical systems, examine the debates it ignites, and glimpse the future it inspires. The story began in 2000, when Sheikh Mohammed bin Rashid Al Maktoum announced a plan to create a signature landmark that would put Dubai on the global map. The goal was not merely symbolic, it was a strategic move to diversify the Emirates' oil-driven economy through tourism, real estate, and finance. In 2004, the city launched an international design competition that attracted more than 200 submissions. The winning proposal, crafted by Adrian Smith at Skidmore, Owings and Merrill, featured a Y-shaped floor plan flanked by 3 reinforced concrete wings. This geometry was chosen to reduce wind vortex shedding, a critical factor for structures soaring beyond 800 meters. Groundbreaking took place on January 6, 2004, and the project quickly became a testbed for new materials, construction techniques, and project management tools. At the heart of the Burj Khalifa lies its buttressed core, a hexagonal arrangement of high-strength concrete shear walls that rise as a single, tapering spine. The 3 wings act as external buttresses, channeling lateral forces inward and allowing the tower to resist winds up to 240 km per hour. Over 330,000 cubic meters of concrete, pumped at temperatures as low as 5 degrees Celsius to ensure optimal curing, form the skeleton. To complement the concrete, more than 31,000 tons of steel rebar were strategically placed to provide ductility. The tower's exterior skin consists of over 26,000 reflective glass panels and 15,000 aluminium cladding pieces, each prefabricated to tight tolerances and installed by robotic lifts that move up the facade like a giant, vertical assembly line. Beyond the static structure, the building's mechanical systems are a marvel of vertical logistics. The Burj Khalifa houses 57 high-speed elevators, including double-deck units that travel at 10 meters per second. These elevators are coordinated by a skylobby system, where passengers change cabins at the 127-meter and 252-meter levels, effectively segmenting the vertical traffic and reducing wait times across its 163 serviced floors. The HVAC strategy combines variable frequency drives with seawater-cooled chillers, delivering conditioned air while cutting energy consumption by roughly 30% compared with conventional high-rise towers. Water reclamation is another key feature. Condensate from the cooling system is captured, filtered, and reused for the tower's extensive landscaping, saving around 15 million liters of fresh water each year. A sophisticated building management system monitors structural health, wind pressure, and energy use in real time, feeding data to an on-site control center. The Burj Khalifa's impact is measured in both numbers and controversy. Economically, the tower has become a tourism magnet, contributing an estimated $2 billion annually to Dubai's revenue through observation decks, luxury hotel rooms, and high-end retail. Its iconic silhouette has also boosted the city's brand, attracting multinational corporations to establish regional headquarters within the surrounding downtown Dubai district. Critics, however, point to the tower's massive embodied carbon footprint, estimated at over 1 million tons of CO2, and question the social equity of such an extravagant project in a region still grappling with housing affordability. The debate extends to engineering ethics. Does the pursuit of record-breaking height justify the resources expended, or should the focus shift toward sustainability and resilience? Looking forward, the principles pioneered by the Burj Khalifa are already shaping the next generation of supertall structures. The Jeddah Tower in Saudi Arabia, slated to exceed 1 kilometer, adopts a similar buttressed core but integrates a more aggressive taper and advanced damping systems. Dubai's own Creek Tower proposes a spiraling exoskeleton that could further reduce wind load while offering flexible floor plates. These projects echo the lessons learned in Dubai: the importance of aerodynamic shaping, high-performance materials, and integrated building systems that balance ambition with efficiency. In closing, the Burj Khalifa stands as a testament to human ingenuity, a structure that pushes the limits of what is possible when vision, technology, and daring converge. Its engineering legacy will influence skyscraper design for decades, serving both as a benchmark of achievement and a catalyst for ongoing discussion about responsible construction at extreme scales. Thank you for joining us on this deep dive. If this series gave you value, subscribe. More deep dives coming every week.